Okay, so the next thing, I'm going to now do another very similar example, okay, to convince you that this is right. Have you all finished copying first? Yes? Okay, so now let's say now I turn the structure upside down. Right? I turn the structure upside down. This is known as my alpha. This is known as my point I. Okay? So let's say we put us in a situation, you have graduated from McMaster. This is 5 years down the road. You landed up yourself in a 120,000 annual salary job doing structure analysis. And this is your first problem. And then you realize that you're going to calculate the normal stresses in alpha at point beta. Then you start writing the stress X is equal to mz over IZZ multiplied by Y. You forgot about your negative and your positive, or why is it negative? So maybe you remember negative, but you don't know. So everything is compression. You forgot about why positive, why negative. So what as mechanical engineers we do? We look at how the structure is bent. We know that the moment is acting this way, right? This is our moment in Z. And I remember, Eugene tell us the head of the moment vector is always in compression. The tail end of the moment vector is always in what? Tensor. So now you already know from here, you can write down that stress X at point alpha is equal to positive mz over IZZ multiplied by Y. Stress X at point I is equal to negative mz over IZZ multiplied by Y. So what do you think? Good idea or bad idea? By just looking at the where? No. Bad idea? Good idea? Bad idea, why? Alpha is in tension. You okay? Yes. So why do you say opposite? It's okay. I also hallucinate on Fridays, okay? Hey? No, he was not sleeping. I was here looking at his eyes, his cheeky soul. Okay? Someone behind over there, put up your hand. Are you okay? Yeah, but let's say if you forget that the generic equation has a minus sign, right? Let's say you forgot that there's a minus sign down here, right? And why is this y, right? Y positive or y negative? Another way of doing this is by visualizing the deformation pattern. Okay, a lot of times I can't remember at all. Okay, but I visualize how the structure has been what? Deformed. Okay, now what I'm teaching you is lifelong learning. Something's easy for you to remember even when you're not doing in this class. Okay, because later on, you are going to, can you remember our introduction? How many formulas you're going to have? A lot. To just solve what? For one what? Problem. These are the methods that I will encourage you to embrace to help you to solve your problem easily. Okay, right. So you get that. Now, the next thing I want to highlight is what are these stresses that we are drawing? Okay, so we have all these stresses. So I'm going to bring back our diagram over here. I'm going to bring back our diagram over here. So for example, if we have a cross-sectional area, so I'm going to draw the cross-sectional area now. So this is my Y, this is my Z, This is my rotation X, right? Then we come over here, right? We draw our structure. Okay, we draw a structure over here. So this is our cross section. And I'm going to draw a line. And this is our centroid. Again, I highlight the centroid is there because it's by visualization, right? The top half and the bottom half, the area are the same. So when it's the case, when we apply the formula, stress or moment about Z over IZZ divided by Y. So this is our axis. This is our stress in X. This is our Y. Okay, based on how the structure is bent, this is how we sketch our stress profile. So we know that okay. So over here, we know that this at this point over here, this is our minus stress X maximum or stress X minimum normal stress, and then this is our stress X maximum. Okay. So when we draw our stress field, okay, how to sketch the stress field? Okay. So to sketch the stress field, there are a few ways that people are doing it, but what I want you to do is follow this notation. I'm going to draw a thick pink line. So this is where the material is. Okay, so this is where the material is. Okay. So on the left hand side, we have compression. Your force, your force or your stresses vector should be pointing towards it. So if the center is the material, to do compression, you have to push into the what? Material. Okay. At the bottom part, it's pulling away, so this is tension. Okay. Now, for this case, can someone tell me where is the position of the neutral axis? Yes. Yeah. So at this point over here, okay, is where our neutral axis. Okay. So in this context, right, under symmetrical or symmetrical bending, okay, the position of the centroid is the same as the what? Neutral axis. Now we specify the neutral axis is at that position because the normal stress in X is equal to what? 0. Yes? Okay. So only under centric symmetrical bending, right? The position of the centroid is the same as the what? Neutral axis. But not always the case where the centroid and the neutral axis have that same position. Not always, only what? Sometimes. So in what situation will you get when the position of the centroid and the neutral axis are not the same? Anyone? Yes. Say it again. So you are saying that we block this from moving, right? Okay, you are right already. You just mentioned Excel. Bang on. Okay. So the answer is when you have an what? When you have an Excel load. And what? Hold on, you're not off the hook yet. What sort of bending do you call that? Yeah, you are right. But what sort of bending will we call that? Is it symmetry or unsymmetry? Ay, 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 ay. You are right. Hey, listen. I like this, okay? Be bold to answer. I want you all to have that confidence. I don't want you all to like to reserve and not sure. As I say, whatever stays here remains here and online. Okay? No, you're absolutely right. I'm glad. Okay. So now, if we have a structure now, okay, if we now have for example, if we have a structure now that looks like this. Okay, so this is our PY. And then we have a axial load, which is our PX. Okay. So this will be our point A. This will be our point B. And this structure will likely fail at point A. Right. So at A, right, we know that we have a moment at the z-axis at point A. And we also have a reaction force known as what? AX. So the normal stress at point X, or in the X direction at point A, is equal to PX over A, right, minus MZ over IZZ divided by Y. Now, some of you, again, in industry, when you're a principal engineer, you forgot about the formula. You deleted the textbook that Eugene helped you to copy, and you can't remember. Okay, so don't worry again. Okay, now this type of loading, we call it eccentric, symmetrical bending. Okay, what do we call it? Eccentric, symmetrical bending. Okay, so you guys seen this formula before? Yes or no? Right? You're like, yeah, seen that before. So this is due to the what? Axial load. And this is due to the what? Bending moment. So I'm going to sketch very quickly. Okay, I know I'm short of time. If there's no one coming into this class, let's go to 6:30. Oh shit, there are people coming in. I can teach this 12 hours a day. I love it. Manufacturing, you ask me to teach 12 hours a day, I'll buy a gun, I'll shoot myself. Okay, now you can see now that this, hold on, bear with me, that this is our centroid, right? So now we are going to sketch Px over A. So this is our shear stress in X. is under compression. So over here, okay, so this is our Y. So what I'm sketching now, this is our stress X is equal to minus Px over A, right? And then due to bending, oh, Eugene, for seriously, rushing, panicking again. Move. Okay, so for this case, and then I'm going to sketch the bending now. Pali. Right? So we are going to have compression. So we have compression at the bottom. So now this sketch over here is equal to stress X is equal to mz over Izz divided by Y, negative. But the actual load, you have to add both of them together. So this is our Y, this is our stress X, right? So if you add both of them together, the slope is the same, but now what happened is this. What happened is this now. Okay, so this is still compression, tension, but when you add both of them together, this is compression, and the top end is tension. So what you realize now is there's a shift in the what? Neutral axis. So now this is the position of the what? Neutral axis. And this originally is a centroid. So when this is the case, where it's eccentric, still symmetrical bending, right? So I'm going to write this last sentence down. So for eccentric, symmetrical bending, the position of the centroid and neutral axis are not the same. Okay. Okay. I see you guys on Monday, 12:30. Have a fantastic weekend and be safe. Okay.